I just posted a link on the side in the chat. If anyone has the chat open, one of the things I'll do at the end of this presentation is do a demo. And if we have time, I can show it in a few different formats. But if you have a preference for Python versus R versus in the browser using our what's called our Flow GUI, just go ahead and vote in that poll, or just maybe comment either way. All right, so I'm just going to go into full screen mode now. Okay, so let's get started. My name is Erin LeDell. I'm the Chief Machine Learning Scientist at H2O AI. And this is the IBM Community Day presentation on scalable automatic machine learning with H2O. All right, so if you're new to H2O, H2O is an open source machine learning platform. And H2O is also the company that produces this platform. And we also have other products as well at this point, but H2O is kind of the flagship or original platform that we produce. So H2O, the company, was founded in 2012, and so it's been around for a little while. And we are advised by a few notable people in machine learning, so Stanford professors Trevor Hasty, Rob Tibshirani, and Stephen Boyd. So if you've ever seen the Elements of Statistical Learning book, that's by Hasty and Tibshirani, and so it's free online if you are looking for a sort of math-focused or stats-focused approach to machine learning. That's a good book. And the company is in Mountain View, California. So yeah, that's kind of about H2O. And then H2O, the platform, like I said, it's open source, so it's Apache 2.0 licensed, which is one of the more liberal open source licenses. That means you can basically use it however you want. You can, build on top of it, and there's really no restrictions there. And so the platform is written, the core of it is written in Java, but we have APIs in R, Python, Scala, and also a web interface that requires no coding whatsoever. And the core of the platform are our own distributed machine learning algorithms. So we have implemented a lot of the popular machine learning algorithms from scratch in Java in a distributed format so that they can be run on large clusters and with a lot of speed. So that was sort of the point of it. And if you've heard of something like scikit-learn, this is kind of a similar idea. So the idea is to have a sort of wide variety of algorithms with a common interface. The difference in our case being that we wanted to make something that really scaled to large data sets and across multiple machines. Okay, so here's what we're going to talk about today. So the H2O platform, I'll go into a little bit more detail about that. And then we'll talk about what is automatic machine learning, or AutoML. And then we'll talk about H2O AutoML, which is the H2O take on automating machine learning. And then I'll talk specifically like how to use the software, what are some tips, and then if we have time, we'll do a demo at the end. Okay, so for those of you who are new to H2O, or maybe just a review, so again, this is a little bit repeating what I've already said, but just to emphasize, so when I say distributed, that means distributed either on multiple cores on a single machine, or on multiple nodes. So if you have, let's say you go on AWS and you rent out, 20 instances and you form a little cluster, you could run H2O across all of that. And these are our own implementations of these popular algorithms, and they're written in Java. And again, we have APIs and sort of all the sort of standard data science interfaces. And another aspect of H2O and why we're able to sort of form a company around this is that we're able to easily deploy these models to production as pure Java code. And so that's kind of one of the key differentiators as well, is if you want to actually, experiment in R or Python, but then you want to be able to, without any extra work, really take these models into production rather than rewriting them in some other language or scalable language, you get the models as Java code, and then you can sort of bake that into your app, and it's sort of decoupled from the H2O infrastructure. You just get basically a file that's a model. Originally, in 2012, Hadoop was a big, deal at the time. So we had originally written these, written this library to be a machine learning library for Hadoop. And then Spark came along, of course, and then that became maybe more popular even than Hadoop. And so we, extended H2O to also work with Spark. But of course, it also just works on your laptop. You don't have to use Hadoop or Spark. It's just, if you already are using one of those systems, it integrates seamlessly into that. And then if you're just sort of a, data scientist who has small data sets, you could run this on your laptop pretty easily because the algorithms are pretty efficient. So even if you have 16 gigs of RAM on your laptop, you can do quite a bit with that. Okay, so here's just a few terms that are good to know when working with H2O. So we have something that we call the H2O cluster. And what that is a just our name for the shared memory process that's running where all of the computation happens. So this is a Java process, and it runs across clusters with shared memory if you're doing multiple machines. And that's where all the computation happens. So that's where all the data is, that's where all the models are, and everything happens in the H2O cluster. So when you start up, working with H2O, the first thing that you do in your R Python script would be to start the H2O cluster. And there's no real limit on cluster size. So if your data requires it, that you can keep adding nodes to your cluster. All right, and so then this other concept that we have is called H2O frame. It's basically just a data frame. So if you're an R Python person, you already know what a data frame is. If you're completely new to machine learning, it's just think about an Excel page where you have rows and columns, and the difference of an H2O frame versus a regular data frame is it's actually distributed row-wise across the different machines if you're using multiple machines. So some rows will be on one machine, some rows will be on another machine, and it's just kind of this abstraction. So you don't actually have to think about that at all. It's just good to know that that's what's going on under the hood. But when you're manipulating the data frames, you don't have to do anything different. It's just all done and handled for you. Okay, so typically, H2O could be considered sort of a big data engine, but it's really, its primary focus is that it's a machine learning engine. So, so in terms of machine learning features, what do we have? So we have a bunch of supervised and unsupervised machine learning algorithms. So some of the ones that you're familiar with, these are all acronyms here, but GBM is gradient boosting machines. That's probably one of the most popular algorithms that people use. RF, random forest. DNN stands for deep neural networks. GLM, generalized linear models. Stacked ensembles is something that maybe not everybody's heard of, but it's a way to combine multiple models into one sort of super model. So we have a bunch of different algorithms that you can choose from, and then we other things that we do. So by default, we'll handle all of sort of this basic data pre-processing that you need to do for machine learning automatically. So that would include imputation. So if you have missing values in your data, we can just handle that automatically. If your algorithm requires you to normalize your columns, then we do that automatically. If we need to do what's called one-hot encoding, if you have categorical data, basically what this means is if you have categorical data, you don't have to do anything to it. So if you're familiar, let's say with some other machine learning libraries, like for example, scikit-learn or XGBoost, you would have to take your categorical data and convert it into numeric data in some way. So we do that automatically. So we try to take care of kind of some of the more boring stuff that you have to do over and over again every time you do machine learning. Another feature is something called automatic early stopping. So that's something that most of our algorithms have, and what that means is it's just a way to prevent overfitting. So if you pass it a validation set, we can kind of figure out when to stop training so that you don't overfit. And this is important, especially on something like a GBM, and also for deep neural networks as well. So some of the other things that we do, okay, so in machine learning, you often would do things like cross-validation, grid search, random search. So we have methods to do all of that for you. And then once you train the model, you might want to look at things like variable importance, model evaluation metrics, so how well do your models do, and then maybe you want to plot some things. So we have functions for a lot of that as well. Okay, so that's kind of just an H2O overview. So let's talk a little bit about automatic machine learning and what does that mean? Okay, so this is, of course, this is just my interpretation of what does this mean. This is kind of a broad term. So I kind of try to divide it up into different tasks. So what I would say is, at least in my perspective, one of the main tasks of one of the main tasks of machine learning, and of course then you would need to automate that to make it automatic machine learning, is preparing your data, either getting it into row and column format if you're dealing with standard supervised learning algorithms. That could include generating features or feature selection, any of that stuff. And then once you have the data situated, then your job is to generate a bunch of models. So typically people don't just train one model and stop and call it a day. They might train a lot of models, maybe even 100 models, maybe 1,000 models, depending on how how desperate you are to get that performance and what you want to put into it. So the act of generating a bunch of models and either choosing a single model from that group as your the one that you want to use in production, or this last part is sort of an optional part of automatic machine learning, but it's a part that I think can be helpful, as would be ensembling all the models together or some subset of the models together. So if we want to sort of define automatic or machine learning as the way to sort of get the best performance possible in sort of the shortest amount of time, and if your goal is really performance and not something else sort of orthogonal to that, like model interpretability, then what you would want to do if you really cared about performance is also ensemble together. And when I say performance, I mean model performance. So there might be other things that you would value, such as prediction speed. So if you wanted prediction speed to be the fastest possible, you would probably not do an ensemble. You might just choose one model. Okay, so here's the three things broken down a little bit further and with some specific examples. So so for data preprocessing, again, that's like imputation, encoding, standardization, could be feature selection or feature extraction. And then there's all different ways that you can encode categorical features that can really, contribute a lot of value to your model and add a lot of information. And this is kind of one of those things that if you're familiar with Kaggle.com, the data science competition website, you see a lot of this on there. And when I say this, I mean different types of encoding of categorical features, and especially if you have a column that has a lot of categories, like let's say zip code. There's I don't know how many zip codes there are. There maybe like 50,000 zip codes. Like you want to do something with that data, because as just in the raw format, it's going to totally confuse or overwhelm a machine learning algorithm with 50,000 categories. So yeah, those are some aspects of data preprocessing. Then in terms of model generation, there's a lot of different ways that we can generate models. So what we call like regular grid search or Cartesian grid search is sort of a standard, and then we could have a version of that which could be called random grid search or random search, where you sort of randomly sample from a grid, or you randomly sample from, you know, a parameter space to train models. And then another technique is called Bayesian hyperparameter optimization. So that's kind of a different approach to model generation, and it's more of a sequential approach where you train a model and you sort of learn something about how that model did on those set of parameters, and then you feed that information into an additional model that will help you decide the next set of parameters, and then you repeat the process and you tell it how it did on those set of parameters, and then you go forward and you kind of successively get closer to an optimal model. So that's just another way to get a bunch of models. And then I mentioned this earlier with early stopping, so individual models can be tuned using a validation set. So that's not in the sense of generating a lot of models, but that's more model tuning. So individually tuning the models, I would consider part of the model generation process as well. And then if you're so inclined, you can you know, apply different ensembling methods to the models that you've generated. So you know, there's a lot of different ways to do that. I'll just mention two. So one way is called stacking or superlearning. So in H2O, we have something called stacked ensembles, and that's what that is. And that's used often in Kaggle competitions as well. So there's some sort of form of stacking involved, and that's generally what people use. There's another one that's called ensemble selection, where it's more of a greedy approach, and you successively add in new models into your ensemble until the performance levels out. So that's just another way to get an ensemble. Some people sort of create ensembles by hand, just, you know, coming up with their own ratios of different models that they want to use, or maybe some people average things together, but those methods don't work as well. All right, so let's talk about H2O's AutoML. So again, AutoML is a generic term, and the term's been around for quite some time, and it can involve anything that sort of relates to automating typically things that are done by hand. So any sort of model tuning or architecture search or hyperparameter search, or you know, some AutoML is more focused on the pipeline aspects, so the data processing. Some is more focused on the modeling aspects. Some is focused on all of it. So yeah, so AutoML should be considered a generic term, and so H2O's AutoML is basically just taking everything that we have in H2O and automating it. So here's that same slide from before, and this time I've highlighted some of the things that that we have in H2O AutoML. So for data preprocessing, we have imputation, one-hot encoding, and standardization, but we get that for free because all of H2O algorithms already have that. Something we're looking at is feature selection and feature extraction, and something that we're currently working on is target encoding, and we hope to have that in AutoML soon. So that would sort of be automatically applied to any high cardinality categorical features. So any features that have many levels, we would automatically apply that. And in terms of model generation, what we do right now is that we do random grid search, and then we individually tune the models using a validation set. And then for ensembles, we use stacking, and random grid search work really well together, and that's kind of why we took this approach. We also took this approach because this is exactly what we already have in H2O, so it really worked well that we had all the pieces that we wanted, and anything beyond this, then we have to build new into H2O. And so I mentioned this, so random grid search and stacking work really well together. So why is that? So that's because ensembles and particularly stacking performs particularly well if the models that are in the ensemble are both, one, individually strong, so these are just sort of good models to begin with. So we're talking about like random forests or GBMs. We're prefer those type of models to like a single decision tree or something like that. So they don't have to be really, really good, but just generally strong. And then if they make uncorrelated errors. So basically what that means is that when a model fails, it fails differently than its neighbor, you know. So what we want is sort of a strong team where people fail in different ways. So, you know, so that's basically to get a diverse set of models, one way to do that is just to randomly generate them. So that's a great way to get a sort of random assortment of models that perform very different. And then we can use what we call meta learning to figure out, that's what stacking is basically. So stacking is a way of learning the best combination of the base learners. And so it's okay if you have sort of bad models in there as well, because stacking will learn to sort of ignore those bad models. If they always do poorly and there's not any certain edge cases in which they're useful, the stacked ensemble will basically ignore them. And so that's so you know, you don't have to be super careful about what you put in the stacked ensemble. It's more making sure you get enough good diversity to start with. Okay, so what is H2O AutoML? So just to reemphasize, so we have basic data pre-processing, and we hope to add a little bit of feature augmentation with the target encoding soon. And then what it will do is train a random grid of GBMs, deep neural nets, GLMs, etc. So we train random grids of all the different algorithms, and then we have chosen what that hyperparameter space is for those grids. So we think that, you know, we've sort of figured out what we think are the right parameters to tune or to search over, and then we've kind of limited the values in which we search based on, you know, our own domain knowledge in sort of data science. So this is based off of basically data scientists at H2O coming up with this. Then once we have all these models, then we can, well, we would tune each of them with a validation set. So that's important so that we're not getting sort of bad models. We're kind of getting the best models that we can with each set of parameters. And then we'll train two different stacked ensembles. So one will be trained with all the models. So if you run it for, you know, 100 models, we would do a 100 model ensemble. But that might not be the type of model that you'd want to put into production, depending on what your, you know, production demands are. So if you want sort of a more lightweight ensemble, we have something called the best of family ensemble, where we take the best from each algorithm class, so best GBM, best random forest, etc., and we make an ensemble just from that, and that would be have 5 models in it. And so that one can be a nice little bit of a boost if you're trying to go to production. But if you really, really want the best performance, it'll probably be the all models that is the best. But you don't have to decide that. So that's what the leaderboard does. So what we get at the end of an AutoML run is we get a leaderboard. And this concept is borrowed, of course, from Kaggle, or a sort of data science competition. So we rank all the models on a leaderboard and choose a winner. And so we do that automatically as well. Okay, so now I'm going to just show you the different interfaces for AutoML. So the first that I'll show, okay, so we have Flow, which is our H2O GUI. So anytime you start up H2O, you'll have a Flow server running. So whether or not you use it is up to you, but so if you start H2O from R or Python, you could still go to Flow and do things and kind of switch back and forth. But if you're, you know, not feeling like coding, or you don't know how to code, or you just, you know, don't want to get into that world, then Flow is really a good tool for you. So so this is what the AutoML interface would look like. So basically you choose certain things. So one would be, you know, basically just point it to the training set. And once you have selected the training set from your, whatever data sets you have available in your H2O cluster, then you tell it what column you're trying to predict. So once we would select the training frame, another dropdown would come up where you would select the response column from all the columns. And then these are all the options that you can choose from. So you don't have to touch any of these. So you could just click build model, the little build model at the bottom, or you could play around with some of these settings. So you can turn on and off different types of algorithms using that exclude these algorithms section, but typically we would recommend people just leave that be to start out, and then if certain algorithms are really not doing well, you could get rid of them. And then the goal here is basically point out your data and tell it how long you want it to run. So one way to do that is you could just tell in the number of seconds that you want it to run. So the default is that AutoML will run for 1 hour and, see how it goes. And then, but if you want to specify the number of models, so that's another way to say how long to go. So if you want to say run for 50 models or 100 models and then stop, you can just use the max models parameter as well. Something to note is that max runtime will overrule any max models. So if you're going to do a large number of models, you might want to change the max runtime to some very large number like 9999999. Otherwise, it will kill the job after 1 hour. And that's just, to prevent you from, running up a huge AWS bill that you forgot about, running AutoML for 2 weeks. Okay, so then we have a few other things like the early stopping metrics. So that's not something you have to think about, but it's sort of fine-tuning things that you care about. So if you we have defaults for everything basically, but if let's say you're doing a regression problem and instead of the default metric for regression, maybe let's say you want to use MAE instead, or RMSLE, or some different metric, you can specify that. So let's say you want to do early stopping by RMSLE, so root mean squared logistic error. Then you can do that, and then whatever you want to score the leaderboard on, that's also important. So we would guess what you want, but if you want to change how you score the leaderboard, meaning you have to pick some metric to rank all the models by. So if you want to have customize that, you can do that there. And then early stopping, we have early stopping for the whole AutoML run itself. So the goal with that is, like, let's say you said max models to build is 1,000, and you probably don't need to build 1,000 models, but you don't know exactly how many you want to build. So what if you sort of leave the defaults, what it will do is sort of evaluate if it's gaining any more performance by continually adding new models. And if it seems that you're not gaining anything by adding more models, it will cut itself off early. So you can always turn that off as well. Some other things are like end folds. So how many cross-validation folds do you want the models to do? And currently, if you want to do stacked ensembles, you have to do cross-validation. So you have to leave that to a number greater than 0 if you or certain, well, technically greater than 1 if you want to do stacked ensembles. Anyway, and there's other things you can turn on and off, like keep cross-validation models. If you want to free up more memory, you can get rid of that. And then you just click go. So no coding necessary. Here we are in R. So if you're familiar with H2O, this should look pretty much the same as any other algorithm. So in R, we would load the library, and then the first thing we would always do when we're working with H2O would be starting the H2O cluster, and that's H2O.init will do that. And to load some data in, we would use H2O import file, or if you already have some data in your memory in R, you can convert that into H2O frames. So train would be an H2O frame. And when we load the file using H2O import file, it will, and it doesn't have to be a CSV, it could be a whole different number of things, or it could be an S3 location or HDFS location. It's a versatile tool. So that will load everything in parallel straight into the H2O memory. So it doesn't ever actually load that data into our memory at all. So it sort of subverts that and just goes right to the H2O cluster. And then the AutoML function, so here we're just showing basically the very bare minimum number of arguments that you could use. So you have to tell it what your training data is, you have to tell it what your response column is, and optionally you could tell it some number of seconds to run. So this would be running for 10 minutes. So technically you could get rid of that max runtime and just say data, and it will run for an hour. And then one of the things that you get back, like I mentioned, is the leaderboard. So that's just available as a data frame once you're done. And then this is the Pythonic version. So same idea, we just import H2O and import the AutoML method, and we start up H2O, import the data using the import file in Python. And then this has a little bit more of a Pythonic flavor, because first we create an object of class H2O AutoML with the different parameters that are specific to the AutoML run, and that like the max runtime, and other things could go in there as well. And then once we do the .train, that's when we actually start the training. And so anything related to the data goes in the .train method. So this is essentially like the .fit method in scikit-learn. We have just a little bit different interface, the way that we the way that we define the data in H2O. And this is a little bit different than some of the R interfaces as well. So what we like to do is instead of having X and Y, where X is the data itself and Y is the response column, we just have something called training frame, which contains all the columns, and then Y is just this sort of column name or column index. And we also have an X argument. So if you want to just take a subset of the features for a particular run, you can define that explicitly using X. So that way you don't have to create different copies of the data, one with some of the columns, one with all the columns. It's just a little bit cleaner, I think, and easier to work with. So you just keep everything in the train frame, and you can use what you want selectively. Okay, so we have the leaderboard, and let's go to the next thing. Okay, so once you're done, then what do you get? So you get this leaderboard, and this is what that might look like. So in this case, this is what this is sort of a subset of what the whole leaderboard would be. There's more metrics, but here's, if you have binary classification, the default metric that we would sort by would be AUC, and of course you can change that, but that's the default. So this would be a small AutoML run of 8 or 9 models, and it did a little bit of a GBM grid search, it did a little bit of random forest, and it had a GLM. It didn't either have time to do deep learning, or that is cut off from this screenshot. So what you see is, so this is actually real results from the Higgs data set, which is a sample binary classification data set. And what we see here is that, GBMs were kind of leading the way here, and the stacked ensembles were the best, and the all models ensemble was the very best, followed by best of family. And if you'll look at kind of the numbers here, like an AUC of almost 0.79 for the top one is quite a bit better than the top single model, which was that GBM there with 0.78. So on a Kaggle leaderboard, that would be something like, hundreds or maybe 500 spots on the leaderboard between those two. So if you're have only worked with just individual models, stacked ensemble is a great thing to explore. So you can just skip sort of all the more difficult ways to add performance to your model, like feature engineering and stuff like that, and just kind of let the modeling do that for you. But I mean, of course, the best method would be concentrate on all the different ways that you can add value to your model. But this is just the easiest one, because you have all the models already. All you have to do is run a single command to do the stacked ensemble, and you instantly get better performance. Okay, so here's some pro tips. So, all right, so this is before you want to launch your job, what to know. So a few tips about the input data. So we have three data frames that you could provide AutoML: training frame, validation frame, and leaderboard frame. Leaderboard frame I wouldn't use unless you have some specific reason to do that. That's provided explicitly so that you could score the leaderboard on some specific piece of data that you care about. But unless you know that you need that for some reason, the default would be that we would just use cross-validation metrics on the leaderboard. And so that in that sense, you're not sort of wasting data just to score a leaderboard. So in the examples I showed, you really only have to provide a training frame. But what we'll do is we'll chop off a piece of your data to use for validation. So yeah, so remember how we're individually tuning the models, and we do early stopping on the grids and on the AutoML run itself, and we do all that with a validation set. So if you don't like the proportion that we're giving it, so that we would chop off 20% of your data for validation, if that's too much, and I think it actually probably is too much, I would maybe choose more like 10%. Maybe we'll change that in the future. Then you can just split your data however you want using the H2O split frame function and pass along a validation set manually. And so you have control over what is used and how much data is used. Okay, so if you have sort of non-traditional types of data, so let's say traditional data is sort of dense numeric or categorical data. So that's what we typically see in business use cases and a lot of different use cases. But if you have let's say very sparse wide data that maybe you got from tokenizing text or using word2vec on text or something like that, then that's something that you might want to play around with the exclude algos. So you might want to just give it a go on the defaults, but if you feel like maybe it's too many features to handle, it's too wide to handle for the GBMs or random forest, you could turn off those algorithms and then let GLMs and deep learning go at it. So this is probably stuff that we will add automatically. So this could be a case of feature selection or feature extraction, which we could of course automate. So, but we give you these tools so that you can tweak things how you like. So we like everything to be automatic, but we also like everything to be tweakable. So, and let's say you're really noticing that your data does great on GBMs and random forest, and you don't really want to bother with GLMs or DNNs, then you can turn those off as well. But one thing to think about is don't just assume that, try it out, because sometimes having what you would think are bad models like in your ensemble actually help. So that's something to just try out and just see if it works better one way or the other. Okay, so I mentioned this already, but AutoML will stop after 1 hour. That's the default unless you change the max runtime seconds. So another thing to note is if you're caring about reproducibility, so then I would suggest using max models instead with a seed, because max runtime seconds, that the amount of work that could be done on your machine during a given time is not something that's fixed if you have other things running on your machine. So if it was able to do X number of models, in one case, if you give it an hour a second time, might be able to do more models or fewer models depending on the resources of the machine at the time. So if you want reproducibility, use max models and a seed. And so as we're talking about running a lot of models, so something to think about is memory. So eventually, you're gonna, if you run AutoML for however long, let's say you run it for 1,000 models or 10,000 models or something like that, you need memory to store all those models. So so that's something to think about. So one is you need to have enough memory in your H2O cluster to store all the models. And it's kind of hard to estimate that beforehand to know exactly how much model, memory you would need. So, I would just say give it whatever you have on your machine, on whatever machine you're working on. And if that doesn't suffice, then either you could click the button to not save the cross-validation models. That will save you a lot of memory. And if you're doing like 5-fold cross-validation, it should save you about, 5 times the amount of memory to do that. So that's an easy way to give yourself more space. And then, if that doesn't work, you could try a different machine. The other thing you can do is you can run AutoML with a different seed, like maybe run it for so long with one seed and see, what the best model is there, and then clear out all the memory on your H2O cluster and then run it again with a different seed and, try to get the top model that way. There's different ways to be sort of creative when you're constrained for memory. Okay, so let's see. Okay, so after you have hit the AutoML red button, what do? Well, one, you just wait, basically. So you could take a nap. But yeah, once it's finished, there's some things that you could examine to, if you're not happy with the results, or if you think it didn't go long enough, you're expecting it to go a longer time. Then I would look at what the early stopping is doing. So you could turn off early stopping, or you can tweak these parameters. And I'm not going to go into a whole lot of detail about understanding these parameters, because these are explained in the H2O user guide, and all of our algorithms use the same exact terminology and parameters. So there's something that we call stopping rounds and stopping tolerance. But essentially, if you're, if you think it's stopping too early, it's too eagerly stopping, then you can increase the number of stopping rounds and or decrease the value of stopping tolerance. Those are two things to use. And that probably doesn't make sense if you've never seen this before. So just don't worry about that too much. And if you want to run AutoML, let's say you don't want to wait around for 1,000 models, maybe you want to just try it a little bit and see how it goes. And then what you can do then is you can use the project name argument. So you could give it a name. It's sort of like an ID for that run. And then you can run AutoML once and look at your leaderboard and see how it goes. And then if you think it's good, but maybe you want to keep running it longer, you don't have to start over from scratch. You just run AutoML again using the same project name, and it will add models to your leaderboard. So let's say you want to start with 20 models, check it out. You can stop the process, and it sort of allows you to look at the leaderboard, and then you just basically copy that same code, run it again. Make sure to change the seed though, because if you do hit the same seed twice, then you're running the exact same 20 models the second time around. So that's the only advice about that. And so saving models. So all of these models that you've created, you don't just get a leaderboard. You actually have all these models, and you can use any of them if you want. So so if you want to save them, this is just typical, like how do you save a model in H2O, basically. There's a couple different ways to do that, and that's something you can read in the documentation. You can save it as a binary file if you're just kind of, want it for inspecting later, but if you're ready to go to production, we would recommend that you save it as what's called a Mojo file. Anyway, that's all stuff that you can read about more in the user guide. All right, so let's just look at some code. So we have a tutorial here. So let's see here if anyone has voted this. Let's see. I don't know if anyone has bothered to vote in this. Okay, a few people. Okay, so looks like more Python people, but you know, quite a few are as well. All right, cool. So why don't we start with Python? And let's see. So on the slides, which I think if I look here, I don't know if you all have this button, download conference presentation or not. I think you can download the slides, but what I was going to do is click on this link here, tinyurl.com, AutoML-H2O World 17. So in December 2017, this is kind of the first big sort of launch of this well, not the first time we launched H2O AutoML, but really some of the big features got added in this release. And we made a tutorial, and that's located. Let me go back here. So that's on our GitHub. So, all right, so there's a whole bunch of tutorials in here. And while I'm just sort of describing how to learn H2O, I just want to say docs.h2o.ai is the best website to go to. So this is where everything is. And the main thing that you want probably is the H2O user guide. So you click on that. And then there's docs about all of our different products. So H2O Sparkling Water is the Spark package for H2O. Driverless AI is a proprietary AutoML solution, which has the same sort of goal of H2O AutoML, but with some really advanced automatic feature engineering and visualization and other features that, including GPU support, that we don't have in H2O AutoML. H2O for GPU is basically open source H2O, but for GPUs. That's a very new project. And let me just scroll down here. We have sort of tutorials and booklets about different algorithms that we have. And since there's a lot of Python people listening, we have a Python module, like the sort of reference documentation. This is not as comprehensive as the H2O user guide, but this will give you all the methods that you want if you want to look up specific methods and look at their technical documentation. This is where you would go for that. Okay, and so here's just a few sort of highlights of tutorials, etc. So let's go back to this repo here, and this is kind of the best. There's almost too much stuff in here, especially in this tutorials folder. So if you can kind of go into the weeds if you just start poking around. So we kind of highlight some of the main tutorials that we like people to look at. So we would click on H2O AutoML in Python. And actually, this just brings us to the AutoML in either Python or R tutorial. So we have links to both, and it's the exact same tutorial. So we have two versions here. So one we have a binary classification problem that we'll look at, and then two would be a regression problem. So let's look at this one here. I think I already have it open. H2O AutoML binary classification demo. So, all right, so this is, I'm not actually going to run this code. I'm just going to sort of scroll through the Jupyter notebook here. So let's just do that. Let's make it a little bigger. Okay, so let's import H2O, import AutoML, and start up the H2O cluster. So this kind of like not very good looking output here basically is just giving you some information. It's saying I'm going to look for an H2O cluster if it's already running, and I'm going to connect to that one at the default parameters here, which is localhost port 54321. And it says, oh, I didn't find a cluster, so I'm going to start one. So it'll give you some locations of standard out files. This is sort of for debugging, that type of thing can be helpful. But here's a more nice looking version of what you want to look at here. So so this says the uptime, which version of the H2O cluster it is, so which version of H2O this is, how old that version is, how many nodes. So nodes is, I'm running this on a laptop, so I have one node. The default amount of memory that H2O is giving itself when it starts up is 4 gigs. But of course, you can increase it and probably should increase it if you have bigger data. And I'm running this on a laptop, so we have 8 cores, or, on this particular laptop, and, some other information. It says what Python version it's running. So this is kind of an over-engineered example of how to get data. So this was done for a demo where we used Docker. So first it was looking to see if this path existed locally, and then if it couldn't find it, it was going to download the data from the internet. So in the examples, I just had a CSV file. So another thing you can do is you can put just a URL to a CSV file. So basically that's what that is there. So this is, don't look at that too much. So we do importing the data into H2O. And so now we can look at this data frame just sort of like it's a pandas data frame. So what we've done is sort of try to implement most of the common pandas methods. So you should be able to be familiar with how to navigate an H2O frame. We don't have every single thing that's available in pandas, but if there's something that you find that you think should be there and we don't have, you can just tell us about it. You can create a Jira ticket, or tweet at us, or make a go on our Google Stream, or a bunch of different ways, because we like to hear about stuff from users. So this will just give you some information about the data. So this is a data set where we are predicting product back orders. So this is given some number of product metrics such as current inventory, transit time, demand forecast, prior sales. We're going to try to predict if a product will be on back order in the future. And we have 19,000 rows, 23 columns. Here's kind of a sampling of what these columns look like. Just kind of basic business data. Okay, so like I said before, the way that we tell H2O what the response column and the predictor columns is using these X and Y variables. So Y would be response column, which is went on back order. In this case, in this data set, we have almost all the columns are going to be useful except for one, which is an ID column. So this SKU column, that's this sort of a product ID. So we're going to want to remove that from our set of predictors. If you leave it in, it probably is fine. It's going to get ignored by the algorithms anyway, but just to sort of be principled about what data we're putting in, let's just remove it. So X is going to be all of our columns. Let's go ahead and remove the response in the SKU column. So now X will just be everything except for the response in the SKU. So here we're going to run it for 10 models, and we have our training frame, and then it gives some progress bar, and it will finish. And I think on a laptop this would take a few minutes to run. All right, so now once it's done, then we would just want to look at the leaderboard and see how we do here. If you're doing sort of real data science, you might want to try more than 10 models. This is kind of for demo purposes. You might want to try at least, maybe 50 models or something like that. And yeah, so that's just sort of something to note. And here's what our leaderboard looks like. So what we see is the stacked ensemble all models is on top. with an AUC of 0.947. And then what we see, which is somewhat unusual but not unheard of, is that there's a GBM that is in number 2 instead of the sort of lightweight stacked ensemble. They're pretty close in performance, but this is why it's good to trust the leaderboard instead of something you think that you might know in your head that you think a certain model will do a certain way. So leaderboard will tell you for sure what's going on. And remember, these are cross-validation metrics. So anyway, this is our leader model here. And again, if you wanted to choose the best GBM instead of the top model, that's totally fine. It just depends on your use case and what you're looking for. That shows just the head of the leaderboard. Let's look at the whole thing. So here we see some interesting results that we get a few really good models and then it kind of drops off, and some bad models down here. GLM, really big, drop off after the tree-based models, and we didn't give it very much time, so it only did one deep learning model, and that one didn't do well at all. So that was unfortunate. And so one other thing that I only have a few minutes left, but one thing I want to just point out, because I think it's kind of interesting, is if we want to look at how does the ensemble work here. So one thing that we can do is, I'm not going to go through all this individual code, what it means, but let's just scroll down to what we see below, and you can read more of what I'm skimming over later. But basically what I wanted to show you is how do each of the models contribute to the ensemble. And so what we can do is the meta learner model, which is the model that learns how to best combine the base learners to predict the outcome. What that model, that's just any old other model. In this case, it's a GLM. So we could just look at the coefficient magnitudes and how it's sort of valuing the input. And so the input are actual models. So what's kind of interesting is it's valuing this XRT model. That stands for extremely randomized trees. That's just a variant of random forest that we have in here. Then this GBM, which was the number 2 in the leaderboard, is doing well here, and a couple other GBMs. And you can see it's completely ignoring the input from the deep learning and this really bad GBM model down here. So remember, when you do a random grid search, you're going to get some models that are bad. So even though it's a GBM, GBMs are usually good. This particular set of parameters was not good. All right, so I did run out of time, but you can check out the R tutorials as well. Flow, let's see, this is the same thing in R. Documentation, how do you download H2O? That's a good question that no one asked, but I'll just announce. So one is you can, if you're an R user, get it from CRAN, just like you would any other package. It's called H2O. If you're Python, you can get it from PyPy, just pip install H2O. Now, if you want to always make sure you have the latest version, or if you want to use the nightly version. So we release a new version every single night, and our major releases go once every 2 months or so. You would click latest stable or nightly bleeding edge, and it'll bring you here. This is if you want to use Flow. All you do is download this zip file and then start up H2O using this command, and then type in localhost 54321 in your browser. And I think I'll wrap it up. Let me see. Here's some links. So if you want to download these slides later, here's all the links to H2O stuff. I will give people a second to screenshot that if they want. And please, if you're interested in contributing, get in touch. We would love to have more contributors to H2O in any language or documentation even. And that's how you can find me on GitHub or Twitter. That's my email address. and a sort of out-of-date website. So thank you very much. And I think I'm done. I'll just see if anyone has any questions. Okay, let me just go. Do we support PMML? No, unfortunately we do not. And we don't have plans to do that either. So that is, somebody prefers Erlang. Well, we don't have an Erlang API yet. Let's see. How about importing existing DNN models from TensorFlow? Can't do that actually. So H2O AutoML runs entirely on the H2O stack. So so basically, yeah, so there's really not a way to do that. And if you did want to do automated machine learning for TensorFlow, that's basically a service, or like this, I don't know if it actually exists yet. I don't think anyone can get access to it, but Google has an AutoML thing where they basically do architecture search. That would say the closest thing to that. And how much implementation overhead is necessary for installing H2O on an existing Spark cluster? I would say very little. H2O is just a Spark package, so it just gives you access to all the algorithms in Java. And it's meant to work seamlessly with Spark. Okay, so all right, I will wrap it up now. And again, please get in touch if you have any questions, and hopefully these slides will be available. And just if you want to find them later, let me just leave a link here to where we have all of our slide decks. If you ever need to find them. Okay, all right, thanks a lot. Goodbye.